So, capacitors. When we start talking about capacitors, it's kind of like, what? I don't even get it. Why are we doing capacitors? It turns out that there are some really important things about capacitors, and I think let's just get into them and start working on them. And the basic idea of a capacitor is two parallel plates that are separated by, let's say, nothing. There's vacuum in between them. Okay, so one plate they both have the same size area A, and they're separated by a distance S. Now that's a parallel plate capacitor. This is an actual capacitor. I just grabbed this one. Let's see if we can see this. Can you see that? It doesn't look like a parallel plate, but that's one that you would see in real life. I think this is a capacitor. Here's another one, a tiny little one. So they come up all over the place. So let's say I look at this from the side. I have here, this is a battery. And I know we haven't really done circuits yet, and that's okay. Here's a battery, and then I have some wires connected to these two parallel plates. So when I do this, this is the positive side of the battery. Then I'm going to get current coming out this side, and I'm going to have, well, I'm actually going to get negative charges flowing this way. They're going up here. The negative charges get to the plate, and they're like, oh, hey, there's a gap. Well, let's stop. And then another comes up here and they say, okay, move over. So you get all these negative charges built up on that side. But that pushes negative charges away, so they continue down here, and you have a complete current. And then you get leftover positive charges on that side. There should be the same number, and I missed one. So we have plus Q on one side. We have minus Q on the other side. And then eventually the current stops, and you have a charged capacitor. And when that does stop, the change in potential across here is equal to the change in potential across the battery. And the current's 0. And we'll learn about that later. Okay, so it turns out that there's a relationship between the charge on the capacitor, which technically is 0. So the charge is 0. But when we say charge, we mean the net, not the net charge. We just call it Q. It's the value on one side. So it turns out that there's a relationship between the charge on one side of the capacitor and the change in potential. And so we call this relationship the capacitance. C equals the charge on one side divided by the change in potential going from one side to the other. That's delta V. And so that's the definition of we define capacitance to be that, and it's in units of farads. Farad. Okay. And again, you may think, well, what the heck really cares? Well, let's draw this up a little bit bigger. Let me draw a bigger capacitor. So here I have plus Q, and here I have, trying to line it up, minus Q. And it's not hooked up to anything. I disconnected it from the battery. The big deal is that it turns out that this plate, a parallel plate like this, makes a constant electric field near the plate. So we actually get this, a constant electric field, which is super important because we can deal with constant electric fields. And more importantly, the magnitude of that electric field due to the capacitor is equal to Q over A epsilon naught, where A is the area and Q is the charge on one side. And epsilon naught is a constant equal to 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. That's epsilon. This is the same thing in this. K, remember K equals 9 times 10 to the 9th newtons meters squared per Coulomb squared. That is equal to 1 over 4 pi epsilon naught. So that's that same epsilon naught right there. You can actually check that and see if it works, but it's the same thing. And that's why it's Coulomb Newton meter squared, because 4 pi has no units. Okay. Now, what about this is the value for the electric field inside of the capacitor. So if I increase the charge, I increase the electric field. If I increase the area, I increase the electric field. Now let's just calculate the change in potential. Say I want to go from A. Let's see. Let's go from A over here to B over here. So I'm going to go that way. So remember we defined the change in potential is negative E delta R. And so E delta R is going to be negative because cosine theta, actually. So this is going in the opposite direction of electric field, so this part's negative, but then I have another negative sign. And this works if I have a constant electric field, which, boom, got a constant electric field, so I can actually do this. So if this distance is S, then I get delta V equals the electric field, which is going to be Q over A epsilon naught, times the displacement that I did, which is S. And this is the change in potential for a capacitor. If I divide that by Q, then I get, if I take C is Q divided by delta V. Let's do that. I'm running out of room. I'm going to switch papers. I was trying to fit it all on one paper, but there's no need to make things work. So let's say this. C equals Q over delta V. So I'm going to take Q, which I just picked that, and I'm going to use this as my expression for delta V. So I'm going to divide this by QS, and then I'm going to multiply by A epsilon naught. And I get A epsilon naught over S. And this is the capacitance for a parallel plate capacitor. It's a property that depends on the physical parameters of the device. It does not depend on how much charge is on there. That's what we like about this. So it depends on if you make these two things closer together. If you decrease S, you increase the capacitance. If you increase the area, you decrease the capacitance. You increase the capacitance. I got that backwards. Okay, so, but if I change the parameters of this, then I change the capacitance. So there's a definite relationship between Q and the change in potential. Okay, so that's a good introduction to capacitors. Now we can use these. Primarily, the thing that right now we're going to use these for is to create a constant electric field, and that's very useful.